Hey everybody, this is Mr. Schaefer, and I want to welcome you back to just another day where I can present some information to you through a video podcast here where we're going to look at some motion concepts related to calculus. And specifically, I'd like to just walk through a problem with you where velocity is given, and we're going to connect that to displacement and distance, and even look at some average value discussions here at the end of the problem, where we'll bring back the definite integral and try to connect that into where we might see it with motion. So here's the problem. It's pretty straightforward. It says that a velocity is given by an object as t squared minus 7t plus 10 meters per second on the time interval 1 to 4 seconds. So I'd encourage you to have some paper handy if you want to jot down some notes or to try this. That'd be great. You might even want to have a calculator or just access to Desmos where you can graph and examine some of the function's behaviors. And then, of course, the calculator just for some of the integral calculations that we'll get to in a little bit. Okay, so part A says to do this. Find the time intervals when the particle is speeding up. So remember that a particle is speeding up whenever the velocity and the acceleration have the same sign. So whenever they're both positive or when they're both negative. And remember that acceleration is the derivative of velocity, so graphically we can think of that as the slope of velocity. And so what I actually did here is I have a picture of the velocity function that I've graphed here on Desmos. Here's the parabola. T squared minus 7t plus 10. I'm just going to select this graph to get these key points, and I'll select the key points so that we can see kind of where this parabola is. Now I'm looking for places where the velocity is positive. So where is this graph above the t-axis, above the x-axis essentially? But again, only from 1 to 4. So our domain is just from right here along to right here in that section. Well, here from 1 to 2, the graph of v is positive, but notice that the slope is negative. The acceleration is negative. So there I have opposite signs, and I don't want that. If I go past x equals 2, now I have negative velocity, and on this stretch right here before the vertex, I also have a negative slope. So between 2 and 3.5, both velocity and acceleration are negative. Past 3.5 up to 4, the function v is increasing, so I have a positive acceleration, but yet the velocity function itself is below the t-axis. So there I would have opposite signs on velocity and acceleration. So the only time interval on 1 to 4 where the particle is speeding up would simply be from 2 to 3.5 seconds. Part B. Find the net displacement from 1 to 4 seconds. Recall that we learned yesterday that the net displacement formula, if we're given velocity, is to simply find the integral of velocity from 1 to 4. And you can hit Math 9 on your TI-84s to compute that. The velocity function, of course, is given back up here. And so when we're finished, we should get a value of negative 1.5, and the units are going to be meters. If we check this unit analysis very quickly, we'll have meters per second times a small change in seconds. So meters will be our units on that displacement. And displacement can be negative. That's okay. It's just total distance that cannot be negative. Letter C, find the total distance from 1 to 4 seconds. Really very similar to the problem we just did. The only thing I'm going to add is absolute value bars around velocity because total distance is going to always be positive. So I'll write that down here. Part C. Same integral from 1 to 4. Same time interval. But we're going to integrate the absolute value of velocity. So again, you can find the absolute value bars on the TI-84. You'll hit Math 9 to get the integral symbol. But then when you go to type in the integrand itself, hit the math button again, and then just arrow over to the menu item that says number, N-U-M, to find the absolute value feature on the TI-84s. Anyway, type that in, and you'll end up with a positive answer of 5.167. Again, meters would be the units. And then finally this, average acceleration in part D. Now, we've got to be careful with this word average. What that's really alluding to is this idea of average value. Remember that average acceleration, and I'll write that down here, if I use the difference quotient, is really the change in velocity divided by the change in time. So from 1 to 4 seconds, v of 4 minus v of 1, all divided by 4 minus 1. Now that might look to you like average velocity, but remember, if we check this, I have a change in velocity, or meters per second, in the numerator. We're dividing by a small change in time, which is seconds, and I end up with meters per second. That's actually an acceleration unit. So what we have here is actually the computation for average acceleration. But because we don't see delta A anywhere, or A of 4 minus A of 1, we tend to think that what we have is really something different. But this is average acceleration, and if you compute that difference quotient, we end up with an answer of -2 meters per second squared. And then as a little bonus question, what if we just repeat that very same question using a different method? So finally, part E, again, average acceleration. Well, remember the average value formula in calculus. The integral of a function across bounds a to b divided by that interval. That's average value. Well, I want to find the average acceleration, so my bounds would be 1 to 4. The value I'm looking at is acceleration divided by 4 minus 1. Now 4 minus 1 is 3, and division by 3 I can write as 1/3 out in front of this integral here. So there's another way to compute the average acceleration. Type this in on the calculator, and you'll end up with a value, again, of -2 meters per second squared. Remember that acceleration is the derivative of velocity, so what goes here would be the function 2t minus 7, or in other words, the derivative of our given function for velocity. And then finally, I want to make one more connection to this average value discussion here. Remember that average acceleration, here's the connection between these two. There's an expression for the average acceleration of a particle from 1 to 4 seconds, but if I use FTC in the numerator, the antiderivative of acceleration is velocity, and if I plug in the upper bound and plug in the lower bound, using the fundamental theorem, I end up with this. Numerator expression divided by the denominator of 4 minus 1. So here are the two ways to find average acceleration. And they're identical. Average acceleration, this also average acceleration. So two different ways to solve the exact same problem. So I hope that helps. Just a little bit of connections between motions and various concepts. I'll post this video podcast for you soon. Thanks for watching, and good luck to you as you continue to work through these challenging problems ahead.